Hi guys, in today's lesson we're going to be learning about the history of chemistry as well as introducing the scientific method, which is probably not new to you. Most likely you have learned the scientific method before, but we're going to talk about it again today, and we're going to use an example really from my own life, and then I'm going to challenge you guys to do a similar thing and use an example from your own life. So as we're going through today's lesson and as you're listening to the examples that I'm giving, be very wise to be starting to think of examples from your own life that maybe could be applicable to the same process. So we're going to start out by talking about alchemy. When we talk about the history of chemistry, really what we're talking about is the philosophy of chemistry. Back before there were real answers to scientific questions, there were opinions about answers. Questions like, what material is the best? I mean, this is an opinion question, right? This is a philosophical question. What's the best? Well, what's your criteria? Is it the softest? Is it the shiniest? Is it the most dense? Is it the most readily available? Is it the least readily available? Those are all constraints that give rise to philosophical questions, like which material is perfect. Well, alchemists believed that gold was the perfect material for whatever reason. When philosophy begins to end and we start to get the ability to do real science, then we start to see experiments and chemistry begin. At the beginning of chemistry, at the dawn of science, it is no longer about what you believe to be true, and it is now about what the evidence shows. And so as we start to talk about chemistry, we're going to be looking about what does our evidence show. The scientific method is the way that scientists do science. The scientific method is sometimes presented as this like linear thing, step 1, step 2, step 3, step 4. The problem with that is that science doesn't work that way. Science doesn't care what your time frame is or how quickly you need an answer. I mean, we're talking about COVID-19. Science doesn't care how long you have till you want to get back to school in the fall. It takes as long as it takes to do science. It takes as many tries as it takes to do science. You have to be patient. You have to be artistic. You have to be adaptable and ready. And so this picture of the scientific method that I have here is really more about the process, right? You make an observation, you come up with a hypothesis or an explanation, a possible explanation for what is wrong or what is right with whatever you're looking at. And then you've got to figure out a way to test it. Once you've tested the hypothesis, either you were right and you've supported what you think is the answer, or you were wrong and back to the drawing board. It's time to try something else. After that, okay, as hypotheses become theories, as theories become laws, we'll kind of come back more to that. That's really like big science, forming theories, forming laws. That's like something for, way further PhD scientists. For us, in this class, we're really going to be staying in the pink and the blue of this picture. So the making observations, coming up with a hypothesis, testing that hypothesis, and then either allowing it to pass or fail that test. So we're going to be looking at this process, observe and collect, formulate hypothesis, and test. We're going to be looking at this hypothesis from the standpoint of something that happened in my own life. So the other day, my son Mikey came to me with this toy. Okay, so you may recognize this guy. This is Mater from the Cars. And I just want to show you a picture of my cute little guy before we get started. See this little face? He came to me and he said, "Mom, can you please fix Mater?" And so I had a few hypotheses that I needed to test. So I'm using the scientific method here. The first thing I did, as many of you guys would know to do, is I turned over Mater and I found the on-off switch. And so I toggled that, is he, I don't hear anything, I don't see anything. And so then I turn it the other way. Nothing, okay? No noise from Mater. So what's my second thought? Well, my second thought, of course, is, well, the batteries are dead. Sorry, buddy, the batteries are dead. So he says, well, Mom, can you please switch the batteries? So, of course, I did. So I'm going to go. I get my little micro screwdriver, which everyone has now for cars. for toys, and I go ahead and I unscrew and open up Tomater. Next piece of information, I've got some AA batteries in here. So I think, all right, well, I need some new AA's. These are actually the ones that I just recently replaced. Notice Tomater still wasn't working. So if we go and we replace these, now I went and got these out of this bag. This is a bag that just exists in one of the utility drawers in my house. And so I went and I got this bag, and I figured, well, if I get replace the batteries out of this bag, I should be able to get this toy up and running. And so I did. Okay, so I replaced these toys, or replaced the batteries, and it still doesn't work. So, of course, now he went and asked my husband to help. So Mikey went and asked Mike to fix the toy, and Mike hasn't done it yet. So today I'm going to test my next hypothesis. So my first hypothesis was the on-off switch wasn't working. Tested it, false. Okay, fails the test. So now I go back and I say, okay, well, maybe the batteries are not working. So I exchange the batteries, not working. So now I need to think some more. Okay, what do I think could be wrong? And I thought, I just don't know if I trust this bag of batteries. I really have no way of knowing if these are fresh or old. They may have come out of an old toy, got left on the counter, and then kind of swept into this bag. So I'm testing my last hypothesis today, that maybe if instead of using the big box or the big bag, I use a brand new container of AA batteries, maybe that is going to help my Tomater. So I'm showing you that it's closed. I'm showing you that it's closed. I'm going to open up this package. I'm going to get out fresh batteries, and we're going to see if we can get Tomater back working. Okay, so I have my fresh batteries out. I'm going to pull out the batteries of Tomater here, and I'm going to put in my new fresh batteries. Of course, I'm checking to make sure that my positives match my positives and the negatives match my negatives. I got some fresh batteries in here, okay, for Tomater. I still don't know if he's gonna work. Oh, maybe? Did you hear that? There's a little tiny noise. Let's see. Okay. Oh, so I'm gonna put my screw back into Tomater here. Now I have my new fresh batteries from my new fresh pack. I turn on Tomater. I don't know if you can hear it. He's starting to make some noise. I wonder what's going on. Now he's an old toy and he's starting to make some noise, but not enough. So I need to come up with a new hypothesis. Maybe you can think of something. Maybe he's just old. Maybe you have a better idea about what could be wrong with Tomater that I could maybe test again. If I'm out of hypotheses, I can pull this idea back into my scientific method. As I run out of hypotheses, I can say, you know what? When the electricity just doesn't work, Tomater doesn't work. That puts my hypothesis of broken batteries and missing electrical, that puts that into the larger theory of how electricity works and how it powers, and even the laws of electricity that are going to tell me about how you need electricity in order to run a machine like this. So I'm just going to take a second to revisit the different types of data that we could collect. So when we're looking at Tomater in the first place and we're trying to figure out why he's not working, we're going to observe with our five senses. Do I hear anything? Do I feel him rattle? Can I, what are your other senses? So touch, right? Your sense of touch, smell, taste, hearing, sight. Is that all of them? Touch, taste, smell, hear, sight. Yeah, okay. Those are all five of our senses. And so I'm going to use those five senses to try to figure out what's wrong with Tomater. Then I'm going to measure and collect data. I'm not making many measurements except is he working, check yes or check no. I could use quantitative data. I need 3 AA batteries that I need to replace. I can also take qualitative data. Qualitative data is whether or not I can hear him. Other data that's not expressed as numbers. Now, obviously in science, when you're in a lab, collecting measurements of how many ounces something weighs or how many cubic centimeters of volume you've used. All of those things could be quantitative data. If it has a number, it's quantitative data. If it doesn't have a number, it's a piece of qualitative data. Qualitative data is going to express a quality, a smell, a look, how it, if you think that lemon lime Gatorade is yellow or if you think it's green. Quantitative data is going to give you a number, and when you get a number, you can't argue that number. The number is what it is. See, the gold weighs 5 pounds. The volume of the liquid is 10 ounces. You can't argue with that, okay? It's a numerical data. And so in science, we prefer the numerical data just because it's less argumentative. Once you've made your observation, it's time to form a hypothesis. The hypotheses that we went over were first that the on-off switch wasn't working, and that's why Mater wasn't working, or maybe I would say the batteries were bad. That's why Mater wasn't working. Maybe I would say Mater's not working because the batteries I replaced it with were not new batteries, and so on. So I'm going to create a hypothesis that is testable, that is unproven, tentative, or proposed, and I should have a prediction. I should be able to test it. I should know whether or not I'm right or wrong once I've tested it, but I shouldn't know before I begin whether or not I'm right or wrong. It has to be something that has a question to it, where it's not that, everyone already knows the answer. So you first make an observation and then you form a hypothesis. What are you going to test? Once it's time to test, you're going to design and run an experiment that will help you to decide if your hypothesis is supported or unsupported. So in all of my cases, I am unsupported. It wasn't the on-off switch. It wasn't that it needed new batteries in the first place, because even the newer set of batteries didn't work. Mater is not working. There's something more wrong with him in his electrical system. So if I'm going to create another hypothesis and another test, I'm going to have to dig even deeper into what might be the problem with this toy. To create a great experiment, you should have a control group. Control groups can sometimes be difficult. Mater makes a difficult control group, right? I only have one toy. I only have one test. I can't try not replacing the batteries and then replacing the batteries. But what I can do is try to isolate a single independent variable, switch the on-off switch, and then I'm going to analyze the dependent variable. Does Mater work? So that dependent variable, yes or no, does Mater work, is what's going to tell me the results of my test. Another independent variable could be changing the battery. Independent. Then I go back to my dependent variable. Did Mater work? No. Change the batteries again. That's my independent variable. New batteries. Okay, the other ones were sketchy batteries. Now we have new batteries. Does Mater work? Still no, okay, but my dependent variable stays the same. He either works or he doesn't work. Sometimes your graphs are going to look different. Sometimes it's not a yes or no answer, but you always want to change one thing and then check a separate thing, a measurable separate thing. Either Mater's working or he's not. You can organize these observations or data into a claim. The claim is the answer to the question, why isn't Mater working? Okay, that's the question. Can you fix Mater? That's the question. And so my claim could be, if the question is, why isn't Mater working? My claim would be, Mater isn't working because there's something wrong with his electrical, internal. If the question is, can you fix Mater? My answer might be, no. I'm pretty sure this is more complicated than what I can fix. So my answer to that claim, or to that guiding question, would be no. So depending on the question, your claim might be different, even though you're experimenting on the exact same thing, you're using the same data. Your claim might change because of the different question that you were asked. Finally, if the science that you're doing is big enough, even with this example, we can start to construct a model. I could create a model that explains that electrical circuits need to be connected all the way through, and if the electricity that's coming from the batteries is somehow hitting a break in the electrical circuit, then it's not going to allow Mater to continue working. That would be a model of what I'm seeing here that contributes to a theory of how electricity works. Theories can eventually become laws. The difference between a theory and a law is just whether or not it can be proven, like mathematically shown, like you get an answer, box the answer. If you can do that, then something can become a law. In chemistry and in physics, we see lots of laws. We can see more laws, but even something like gravity is only a theory. Crazy, right? Gravity is a theory, the theory of gravity. So if I were to drop Mater right now, we think we all know what would happen, right? Mater should fall, shouldn't he? Yeah, he should. Mater should fall. But I'm not going to drop him because I don't want to break him anymore. But if I let go of Mater and he rose up to the ceiling, then the theory of gravity I would be contributing to falsifying the theory of gravity. And so every time we do an experiment, our results matter. They either support a theory that is known or they stand in opposition to a theory. And science wants you to do both. It wants you to support things. And if they don't deserve your support, science wants you to say so. Okay? So all scientific discoveries are made by testing a hypothesis, getting the results of that test, and then finding out whether or not that result supports a known scientific theory, changes a known scientific theory, or stands in opposition to something that we thought we knew.